This should be a relatively quick one, I think. Just a quick bit of background and so on. Something I only actually figured out myself today is that a pentagon has 5 angles, a hexagon has 6 angles, and a trigon, which we much more familiarly know as a triangle, has 3 angles, and metry is the measurement of. So trigonometry is the measurement of triangles, or the measurements of triangles. So it starts off in right angle triangles. Draw one. So in right angle triangles we have Pythagoras theorem. Let's call the hypotenuse A in this case, and the other two sides B and C, and good old Pythagoras says A squared equals B squared plus C squared. Now that's not really trigonometry yet, but that only holds in right angle triangles, as do the first couple of things we'll talk about. But then we actually get beyond right angled triangles to things that will work for all triangles later on. So that's Pythagoras theorem. I tend to remember Stephen Fry's Hungarian grandfather pronounced it as Pythagoras. So Fry learned it as Pythagoras theorem, and always wondered who this Pythagoras chap was. All right. So in a right angle triangle also, I could go into a fair bit more detail about quadrants, about radians, and about a whole variety of other bits and pieces, but for our purposes here I won't. So in a right angle triangle, and I've drawn them consistently but I needn't, if we call this angle theta, good generic name for an angle, and we'll call this the hypotenuse, which is the longest side. We'll call this side the adjacent side because it's close to theta. It's the one that theta touches. And we'll call this one the opposite side because it's opposite theta and doesn't touch it. And I can't even spell opposite at this point. Then we have the basic trig quantities. Sine of theta, spelled S-I-N-E but abbreviated S-I-N, of theta equals opposite over hypotenuse. In a second I will over hypotenuse. That's how we define it in a right angle triangle. The mnemonic for remembering this is SOHCAHTOA. Sine is opposite over hypotenuse, cos adjacent over hypotenuse, tan opposite over adjacent. So the cosine, abbreviated cos, COS, theta equals adjacent over hypotenuse. And the tangent, abbreviated tan, is opposite over adjacent. Okay, so those are the basic quantities. Now, quite often we use those to do things like figuring out the components of vectors. So if I have, let me draw it the other way around just for fun. No, actually I won't, just for now. So x-axis, y-axis, vector here, angle theta, to work out the component in the x-axis, right, we still have a right-angled triangle. The component in the y-axis, is here, but since this is a rectangle, it's also here. So that's the opposite side. Oh, sorry, I'll stop writing that, the whole word in. That's the adjacent side. And that's the hypotenuse. So the hypotenuse is the actual length of the vector. So in this case, sine of theta, remember sine is opposite over hypotenuse, so sine of theta in this case is going to be y over the, well, let's call this the vector v. It's the hypotenuse of the triangle, but we'll give it a name, is what going to be y over v. So if you want to find the value of v, we can rearrange that to y, sorry, if you want to find the value of y, because that's what we're going to want to find, is the component in the y direction is equal to, multiply both sides by v, y equals v times sine theta. And that should be fairly familiar. We've been tending to write it as uy equals u sine theta. But that's basically a formula that we were using in projectile motion. So, in other words, we've gone from the definition of the sine, opposite over hypotenuse, and then rearranged it to make the thing that we want the subject. So, apologies if this feels like belabouring the point, but just trying to make sure that it's set up well and clearly. There are various trig identities, like, for example, sine squared x plus cos squared x equals 1. Now, we're not going to get into any of that for this course, but there are various ways in which sine and cosine and tan relate to each other. One of the others is that tan theta equals sine theta over cos theta. So if you run into sine over cos, you can just replace that with tan of the same angle. Okay, so that all behaves and works in right angle triangles, but not in other triangles. But the sine and cosine law, or rule probably is a better word, sine and cosine rule work in any triangle. So if I have a triangle that is not a right angle triangle, and I call this side A, and I call that angle A, and I call this side B and this side C, then Pythagoras doesn't hold because it's not a right angle triangle. So I can't do a squared equals b squared plus c squared. What I can do is the cosine rule, which is, starts out similarly, a squared equals b squared plus c squared, but then it goes minus 2bc cos a. Lowercase things are side lengths, uppercase things are angles. So in this case, I can figure out the length of side A if I know, for example, the length of side B and side C and the size of angle A. So it means that we've got something that look a bit like Pythagoras, but that works in any triangle, not just right angle triangles. And similarly, the sine rule is a over sine A equals b over sine B for any two sides and angles. So also equals c over sine C. And we can rearrange that to give the side or the angle that we need to find. So we will definitely use these at various stages in our work as well. So sine and cosine rule work in non-right angled triangles. Pythagoras and sine, cos and tan by definition work in right angled triangles. So hopefully that just gives you a reminder of how we use these trig rules and how we can work with them to resolve things like vectors, lengths, heights and so on. And we certainly use them in the vectors section to solve vectors.